right, thank you. Okay, so you didn't miss much. I just talked about the title, which you already know. What I just said is that in order to understand the technologies that want set out to close some of the gaps that exist within REST, we need to understand what REST actually is. And since these days there's almost no way around GenAI, I thought it would be a good idea to put GenAI onto this talk as well. It's the only reference, I promise. And I asked Claude to describe what REST is. And what he gave me is a pretty good answer. It's an architectural style. So not a standard, it's a style. For stateless and client-server communication model that uses standard HTTP methods and your resources that are represented as URLs. And where it comes from is actually a dissertation of Roy Fielding, who in the year 2000 got his PhD by describing an architectural style for web applications. And a part of this dissertation is the representational state transfer, where he describes principles, he calls them constraints, about how he reasons and argues about communication in the web. And those principles over the years have evolved into a more or less de facto standard. So almost every API you speak these days or that is developed these days is a REST API, with the exception of those I'm going to talk about. And the constraints of REST are, they're pretty intuitive in some way, others are not that much. So the first principle is that there is, it's a client-server architecture. So there's a separation of concerns. Everyone knows that. You have a client, you have a server, the API connects the two of those. The ratio behind this is to just make it to be able to evolve independently and to separate the UI from the persistence. And we all know that from the tiered architectures we see. The second one is statelessness. So no session info should be retained in the communication channel. That's why when you look at the headers that you send, or in general the request, when you inspect the request in the browser console or whatever, you see all these headers in there that are sent with every request, like the JWT if you send a token or some cookie and other information. That's due to the nature of REST, and that it needs to be stateless, and all the state has to be transmitted in the request. Cacheability is built in. That's a fundamental concept of REST for clients and servers. And the concept is that responses that come from the server decide if they are cacheable and how they are cacheable. So you have certainly seen those cache control headers. That's the way a server tells a client, okay, this response can be cached for that amount of time. The fourth one is that it is a layered systems, and that layers should only have to interact with the adjacent layer. So the top layer doesn't need to know about the bottom layer. And that makes it easy, again, to evolve the system independently. And you see this when you think about security or caching. So if you think about token-based authentication, that can be an additional layer. It often is. If you use some sort of API gateway, then there might be a functionality where the token is verified before it is passed on to the business logic. That does not need to happen in your application logic. The fifth one, that is code on demand. When Roy Fielding wrote this, JavaScript wasn't there yet. So, but he sort of foreshadowed this. And these days, this is almost exclusively JavaScript. So you request an HTML page and you get some JavaScript code. That is code on demand. For those that have been in the industry for a bit longer, this could also have been a Java applet like 15 years ago. No one is doing that anymore. And these days, it is mostly just JavaScript. And the interesting bit about this constraint is that it's the only one that is optional. So this one is considered optional according to the definition of REST. The other ones are not. And the last one is the uniform interface. And there's a lot in there. Well, first of all, URIs identify resources. You all know that. You all have done thousands of API requests similar like this. And the idea is that a URI uniquely identifies one resource. And if you interact with that resource, you send representations of that resource back and forth. So if you now want to do a put on a user with the ID 42, you send the resource you want to put at that particular place, at that particular URI. So you send resources to modify, you send a representation of resources to modify resources. You have self-descriptive messages. So the message itself should be decoupled from the way it is interpreted. So that's why you have those content types. That tells the client, okay, there is some message, that is a generic concept, but this is a JSON message. So interpret this as a JSON message or as an HTML message or whatever XML. Same for cache control, that goes into the same direction. The last thing in that constraint is the hypermedia as the engine of application state. Hey to us. That sounds a bit like some death metal band, but it is at the end of the day a fundamental concept that is, although not often found in APIs. And the idea is that the API gives you information about how you can further interact with it. It should be like a map, a dictionary at the end of the day. So you make one request and you get references, links to other parts of the API that might be relevant to continue interacting. This is something I see very rarely in REST APIs, but I think it is a good idea that would make using APIs a lot easier. So if we take all this, then we typically end up with something like this. We have our API, we have some resources defined, we might have some orders, some users, and then we have some operations. We might have a get where you can use query parameters to filter for the name. We can have a post to create new things. Then we have resources on that collection of resources, which we can indent again, we can get, we can delete. And we might have relations between resources. That is what I would call a typical REST API. There are some nuances, some are a bit different, but at the end of the day, this is more or less what you get when you communicate via REST API or with REST APIs. And this has been working well for quite a while. But things changed a bit. So when Roy Fielding wrote his dissertation, IT landscapes looked vastly different. There were no smartphones, there were no IoT devices, there were no smart TVs, there were essentially desktops, maybe some notebooks, and there also was no concept of microservices in that sense. There was just like the server, the backend, not the services. So you had very homogeneous clients. You had monolithic applications and you had static web pages. That all changed with what we call today the web 2.0. So when the web became from just something you consume to something you take part in, where you collaborate and users create content. That caused like much more heterogeneous clients. It led to distributed microservice architectures. And the web applications, the way we interact with applications become much more dynamic. And with that change led to some problems because the established REST style was not well equipped to solve those challenges. And in particular, there were 6 major shortcomings. So first, if you want to have a truly interactive experience for your clients, you need bidirectional communication. You need to be able to send data from the server to the client. There were some workarounds to do this, long polling and so on, but those were rather hacks than really proper solutions. Overfetching and underfetching became a problem. So overfetching is when you connect to an API and you get a JSON object, for instance, and you need maybe out of 10 fields, you need 2 for your use case. That's overfetching. Same for underfetching. So if you require the data from 5 microservices and you now need to send 5 requests to get all the data, if you only send 1 request, you underfetch. You don't have the data to render your web page or to load your client view. Versioning is a pain. So there have entire books been written about versioning of REST APIs, but we're still none the wiser. Do we do that in the header? Is it something that should be in the path? Shouldn't we do that at all? It is still a painful thing to do versioning for REST APIs from my point of view. It's nothing that is really fun. Same goes for endpoint documentation. the very purpose of an API is to make it accessible to the outside world and have others that do not know the inner workings of that API interact with it. So there needs to be some documentation, but there's no standard or no way how to do this in a standardized way with REST APIs. So there have been frameworks. You all have used Swagger and the OpenAI standards and so OpenAPI standards. But those is just like, this is not fixing the root of the problem. This is just like sort of having you feel less pain. There's a lot of HTTP overhead. We saw that earlier. So due to the statelessness, you send your headers all the time. And if you have a large token where you encode a lot of information, this can be quite a bit of overhead, to the point where there's a limit on the size of the headers. And I've seen tokens large enough that it exceeds the size of the headers. And that can become a problem. So ideally, you want to avoid that HTTP overhead if you can. And lastly, the inefficient data format. So this is not an inherent problem of REST APIs, but since we as a tech community seem to have standardized on JSON, it became a problem, because JSON, while it's easy to read for humans, it is not an efficient format. If you have like a list of users, like 100 users in an array, then you have all of the objects in the array have the same structure and repeat the fields over and over again. You have 100 times, you have name, colon, age, colon, and so on. That is not an efficient data format. And the larger the responses got, the more impact this has on the performance. So over the years, since the 2000s, there have been developed a couple of technologies that address some of these pain points. There is no silver bullet that solves all of this, but there are technologies that address some of those. And I want to go through some of those and give you an idea why they have been developed, which problem they solve, and what, from my point of view, of being from AWS, is the best way to run those on AWS. So the first one I want to talk about is WebSockets. And WebSockets actually are a proper standard. They have been standardized by the Internet Engineering Task Force in 2011, and it is a bidirectional communication protocol. It solves the problem of servers and clients being able to both send messages at each other. We could send messages from the client to the server. WebSocket now allows the server to send messages to a client using a persistent connection. It starts off with an upgraded HTTP connection, and the client just sends a request to upgrade the request. If the server accepts the requests, then he responds with a specific HTTP code, 101, and then you switch protocol. Then the client and the server, they negotiate over the existing HTTP connection about the details, essentially, of how this connection should be established. Once the details have been agreed on by the client and the server, the communication switches to the WebSocket protocol. And then there is a persistent connection between both parties where data can be sent from both parties. And this data can be text, binary, or control data. And at any given time, any of the two parties can decide to tear down the connection and to initiate a closing handshake. That addresses two of the main pain points. One, we can now have bidirectional communication between the server, which is a good thing, especially for real-time application. Think of chat applications, for instance. They almost exclusively rely on WebSockets in some form. You don't have the HTTP overhead. You only have the HTTP part when you initiate the request. Once you switch the protocol, this is a different protocol that is based on TCP, and you don't need to send the headers back and forth all the time again. So how do you run this? That's essentially two ways. One is the traditional way that is pretty much the same for regardless of where you run this. You have some sort of load balancer that takes the initial request and then forwards the request to some server. That can be a container, that can be a virtual machine. And in this particular case, it's an application load balancer that takes the initial request, finds a server behind it to establish the connection. And from there on, once you switch to the WebSocket protocol, you have a standing connection between the client and the server in the backend. So the connections are inherently sticky. You don't need to enable sticky sessions or anything like that. That is handled for you. One thing that is important to remember if you run this architecture is that the health check in that particular scenario is not working on the WebSocket protocol, but you need to also provide some HTTP health check. So this architecture is a good choice if you have a constant high volume of messages or you have very low latency requirements. This is like the prime use case for that sort of architecture where you want to have maximum control over what you run. If you have mixed APIs, for instance, in the GraphQL case that we're going to talk about later, that is also a good choice. So if you need an HTTP endpoint and a WebSocket endpoint behind the same API, that is also the way to go. If you have some very specific requirements like very large frame sizes or very large message sizes or very long running connections, this is also a good approach. For all other approaches, there is a more lightweight version, which is essentially a serverless way to do this. There's a solution called the Amazon API Gateway, and that also supports WebSockets. And the way this works is that the client establishes a connection to the API gateway, and for every message that is sent, a Lambda function, so essentially a serverless function that runs code on demand, is invoked and can then trigger your business logic. And the other way around, if you need to send a message to the client, you just need to know the connection ID. You can store them away, the ID away somewhere, and then send out a request to the client. That has a number of advantages. You don't need to manage any servers. It's pay per use, so you only really pay for the resources you consume. And it's overall a very lightweight way to run WebSocket applications. So if you have very spiky or irregular traffic, that might be a good solution for you. Same if you have the situation where a single message from the client can cause a very expensive backend operation. This will scale much better for you because just by the nature of Lambda functions, they are capable of running quite beefy workloads and they can scale a lot better than, for instance, a container. There's less startup time. We can have more in parallel. So that is also a very good use case for that sort of architecture. In general, if you don't care about servers and you just want to run your applications and you want to be serverless first, then this is also a good way to operate because it can often be a bit of a hassle if you come from a serverless world and then you need to manage containers and load balancers. This is always causes friction and needs you to invest like mindshare in things you don't want to do. One thing that you need to keep in mind is there are some constraints, and those are hard limits on the service that you cannot change. So if you want to go in that direction, make sure you understand the constraints you sign up for, because those can't be changed. All right, GraphQL, another alternative. Well, it's not an alternative. We're going to see GraphQL is actually based on REST, but it is a different way to think about how to build web APIs. And I think everyone has heard about GraphQL. And it has taken really the world in storm in the last years. I think it's probably the most important web framework for the last decade I could think of. And GraphQL is actually two things. It's one, it's a query language, so a way how to describe queries and how to interact with a backend. But it's also a runtime that translates these queries into operations and a way to retrieve data from a number of backends. And the problem that it solves is one of the modern problems that we have. We have a multitude of devices, smartphones, desktops, smart TVs, IoT devices, whatnot, and we have a number of backends. And there's data that is in the backends, and each device has a different requirement to get data. So your smartphone might require different data from the backend to display the app than the web app might have. And before GraphQL, you had to do some backend for front-end pattern, stuff like that. That was a quite involved thing to do. You needed to maintain this, and there were changes in the backend. Then you needed to make changes in your backend for front-end. This did not scale well. And if this doesn't scale well for you, imagine the pain that Meta or Facebook at the time went through. And that's why they set out to build GraphQL. And the idea is, as I said, you have a number of data sources and you have different clients that require data from all the data sources to get the data they need to display the content of the application or web app. And with a REST API, well, there's the mobile client that requests the data from data source A. It gets a whole bunch of data, throws away 80% of the data. The web client might need a bit more, throws away half of it. Still, you overfetch quite a bit. You need more data from the blue API endpoint. Again, overfetching. Same for the other data source. Again, overfetching in both areas. So now you overfetched, you got more data than you need, and you also underfetched essentially because you needed to make 3 requests instead of just 1. And that's where GraphQL comes in. GraphQL allows you to create one endpoint, that's your GraphQL server, that knows how to interact with your data sources, and that provides that schema that you require for the data and a way to formulate queries against those endpoints. So what is now happening, your devices, your app or your mobile client or your desktop client, they send a query and they tell the GraphQL endpoint what data they want. And the GraphQL server knows how to get the data from the data sources from here, from here, from here, gets the data, puts it together, and only returns the data that the client requested. So this is a different way of thinking about interaction with APIs. And to enable this, to make this possible, there are a few core concepts that we need to understand when talking about GraphQL. You could easily talk an entire day about GraphQL, so I tried really to boil it down to the basics, and it all starts with a schema. So a schema really describes the structure, the types, the operations, the capabilities of your API. So clients that want to interact with your API, for those clients, the schema is the first point of contact. That's where they get all the information to interact with your API. It describes types, and types are really fundamental building blocks. So the order and the user we saw earlier in the REST example, that would be a type. And you describe what fields are in the type, if they are optional, if they are maybe an array or a list, and so on. And then you define operations, queries to get data, mutations to change data, subscriptions to subscribe to data. And those describe like what can you do with the data, what data can you get, what data can you change, and so on. You have directives. They add conditional logic to your queries and mutations. So think of it like hooks to the operations, stuff you want to do when a query is executed. And then lastly, you have the resolvers. And the resolvers are what interact with the actual data source. So your data source can be a traditional REST API. It can be a database directly. And the resolvers that you define in your GraphQL server, that describe how you can actually query that data, send an SQL query, do an API, a REST API call, for instance. So if clients want to interact with your API, with the GraphQL API, they can then send a query, a mutation, or subscription operation. And as I said, to get data, you can change data, or they can subscribe to changes to data. So whenever data changes, they get notified, and that is based on WebSockets. Then that's then a bidirectional connection that is established, so they get informed by the server about changes to the data. Introspection is one of the best features of GraphQL from my point of view, because it allows developers to really have a documentation of the API via the schema and make it easy to understand what you're doing, what you're querying, and how the supported operations and types look like. So it's not any guessing anymore, like if you don't have a documentation at all or keeping Swagger in sync with the actual API. This is really built into this. Comes from the same data source that is used to actually gate the data. Clients can then specify which fields, so that solves the problem of overfetching. If you're only interested in the name of a user, just put it in the query and then send the query to the GraphQL server. That is, in 99% of the time, that is via a REST call to just a post endpoint. So there is no GET or any other endpoint. It's just a post where you send the query, and in response to that post, you get back the data that matches the query you sent. As I said, subscriptions are possible and they rely on WebSockets, which we just talked about. And that addresses a number of the challenges we see with REST API. So we now can have communication in both directions. We solve the problem of overfetching and underfetching, and the schema that allows us to do versioning, because as long as we don't remove any types, we're safe, because we can add types. The clients that query only the types they need, they don't care. We just can't remove types. That would possibly break things. We solve the problem of endpoint documentation. The documentation is built into the schema via the introspection. So GraphQL on AWS, again, 2 ways, pretty similar to the WebSocket part. There's a load balancer. There's some sort of server container, an EC2 instance, and you have a load balancer that distributes the requests to the backend. And you can offload some of the functionality. So if you have token-based auth, you can offload this. You can have some rate limiting in the load balancer part. Overall, this is not the easiest way. So most customers I recommend to go with the managed way we're going to talk about in a second. There are some use cases where this is still the way to go. If you require the use of a standard open source framework, Apollo is the most popular one. There are others in essentially every language. If you need to do this, then this is the way how to do it. Again, if you want to have maximum control over what you do for whatever reason, or you want to do something out of the ordinary, that is not covered by a managed product like the one we're going to talk about in a second, then this is also the way to go. For instance, if you have very large schemas or if you have very large payloads for your subscriptions, those are things that are sometimes not covered. And there might be a case for you to go that way if you absolutely require this. Also, if you want to do Apollo Federation, you need to use the Apollo framework and host it yourself. From my point of view, the much better way to do this is using AppSync, which is just a managed GraphQL server, a serverless offering that integrates natively with a lot of AWS services, but also can integrate with external services. It is pay per use, so you are built for queries, the modifications you send. So you don't need to manage servers, you don't pay for servers, you just pay for the queries it serves for you. And it is, from my point of view, the best starting point. If you want to build a GraphQL API, I would start there, and only if this does not fit your requirements, change to a self-hosted model. There's a few cool features. You can do rapid development using the Amplify framework, which is essentially a CLI tool framework that allows you to really quickly spin up APIs and web applications. That is relying a lot on AppSync. It has some cool capabilities built in when it comes to offline data synchronization and offline use cases. It is overall a quite nice tool to rapidly build your applications. GraphQL is not the only solution that thinks of querying APIs, that tries to redefine the way you query data using APIs. Most of the approaches that have been developed over the years have been abandoned in favor of GraphQL. These days, there is only one main, I wouldn't call it competitor, but alternative, and that is Falcor. That has been developed by Netflix, which is famously known for the microservice architecture and thus ran into the same problems like Meta did a while ago. Just many different clients, many different microservices, and no good way to sort of map between those. So they built Falcor. It is a bit different. It is not only a bit different, it's quite different. It solves the same problem, but it does it in a different way. So where GraphQL uses a schema, it uses a virtual JSON graph. The query is different. So for Falcor, you send a JSON path expression and it returns just the URI of where the resource can be found that you requested, and then it's the job of the client to fetch the resource, while GraphQL resolves this in the server and returns the result for you. GraphQL is much more standardized. The Falcor implementation is not opinionated in the sense how you should resolve the data. It just tells you what the URI is, and then you need to deal with that. And the biggest difference is the community and the ecosystem. So Falcor is surprisingly big. It has over 10K stars on GitHub. It's probably the biggest repository you've never heard of before, but it's nothing compared to GraphQL. And if I would have, yeah. Oh, that's a good question. I don't know the answer. I think people voted with their GitHub stars essentially. So with the size of the ecosystem. So the pull that GraphQL has, that is for a reason. And if you want to go into the direction of having a query language on top of your APIs, I would always recommend you to go with GraphQL just by the pure size of the community, the activity of the community, and the number of frameworks around this. I'm sure there are some blog posts out there that compare the performance, but I wouldn't know. At the end of the day, it comes down to a lot of details, like how do you implement the resolvers, and there's a lot of moving parts. It's hard to make that comparison. Yeah. So if you want to do this, go with GraphQL. But now you've heard of Falcor as well. Come again? That's the one by Microsoft, right? So I didn't include it here because it feels pretty much dead outside the .NET space. So there's not much happening. That was something standardized pushed by Microsoft for quite a while, but I haven't seen any of those APIs in the wild, and it's more of a specification than a framework, I would say. But yeah, something to keep in mind. That it goes in the similar direction. You're right, but I didn't include it here. Yeah, another framework that I find quite interesting and that has a widespread usage today is MQTT. So the message queuing telemetry transport. It's a lightweight messaging protocol, and that has really been designed for efficient communication in constrained environments. It has been, the development actually started before the REST standard was published, but it was only standardized like 10 or 12, yeah, in 2013, so almost 10 years ago. And the concept is quite simple. There's a broker, and that broker, as the name implies, brokers messages between clients. And clients can either be publishers or subscribers. And the way they communicate is via topics. Those topics, they live in the broker. And that gives you a publish-subscribe model with hierarchical topics where you can have many millions of topics and clients that interact via the broker. As I said, it has been designed for resource-constrained and low-bandwidth networks, which today is I would say 95% IoT devices. So this is pretty much standard in IoT devices, where you have some publisher, some devices that publish, some devices that are subscriber, both are clients. Then you have a broker in the middle. You have topics, they can be hierarchical, and subscriptions can be using wildcards. So you can subscribe on all the topics that are prefixed by topic /, or you can subscribe on a particular topic, like only topic A, and then the broker pushes messages that are sent to those topics to you. You have different levels of quality of service. So you have different semantics, at least once, at most once, and exactly once, all with different trade-offs, but they are there. They are part of the standard. It has seen widespread adoption IoT applications, and it is based on TCP. It can run over WebSockets, but this is only really used if you need to connect to some web client. So it's rather an edge case. Most of the time it's running over TCP. This again, it solves the problem of not having a way of doing bidirectional communication. So now the server can send data to the client. Whenever a message is published to a topic, it checks the subscribers on the topic and it pushes the message out to the subscribers. It reduces the HTTP overhead, similar to WebSockets. And to run this on AWS, you know that slide by now. The load balancer approach, that is pretty much, you can do everything essentially with that one, where you have a load balancer, you have an MQTT broker. It's very rare that customers do this because this takes a lot of work and you gain very little. It's, again, something you do if you have some edge cases, if you absolutely need to use an open source framework for whatever reason, or if you have some extraordinary requirements when it comes to scale or message size, or if you again want to have the maximum control over the broker. Much better way, which I would say 99% of the customers I see use, is AWS IoT Core. That is a serverless service that is fully managed, that gives you a wide range of features in the IoT space, in particular related to MQTT. It easily, scales to millions of clients and millions of topics. So we have very large customers, Volkswagen using it for the IoT platform and so on. So it really scales well, and it is pay-per-use. And again, you're not going to manage any servers with this. You're just going to have the service scale for you, scale from 1 to 1 million and beyond. You can use rules to forward messages. So you can then be a subscriber on the messages essentially. So when a message comes in, you can send it to a wide range of endpoints, a database, an Amazon S3 bucket to just store it away, a Lambda function to execute some logic on the message that is coming in. And that allows you to build very powerful applications in the IoT space. Think of IoT devices sending telemetry data that you want to send to some database or analyze or whatever. Those are the sorts of workloads where this really shines. It supports MQTT 3 and 5. I put an asterisk behind this because there are some parts of the specification where we deviate. They are well documented. For most workloads, it shouldn't be a problem. If it is, then yeah, then you need to sort of pivot to the other architecture I just talked about. There are a few things that you need to keep in mind. So the message size, there's a limit. The concurrent connections are per account. So if you have one AWS account with many brokers running in it, they might compete for the connections. The number is very high, so it's rare that we see issues with that in practice, but that is something to keep in mind. And if you need really some of the features that where we deviate from the MQTT standard, that's something you should be aware in before using this. So, and lastly, I want to talk about gRPC. So gRPC there are two ways to look at gRPCs. One is from a more technical perspective. It is a framework to do remote procedure calls. The G stands for Google. That's where that originated, but it has then been donated to the Open Source Foundation, and gRPC calls itself a high performance RPC framework. The other way to look at this, what it is used for. And these days, its primary use case is low latency, high performance communication between microservices. So if you have an EKS cluster with a number of containers running, if you want to optimize for latency and performance, gRPC is a good way to do this. The way it addresses a few of the shortcomings by REST. Again, it addresses the bidirectional communication part. It allows for versioning, endpoint documentation. It reduces the HTTP overhead, and it also addresses the inefficient data format. And the way it does this is by defining, you could call it a schema similar to GraphQL. It's the proto file. It uses protocol buffers, and that's where you just define your service. You define how an RPC call can look like, how a message can look like, and then based on that file, you generate code. And you can generate code for many, many languages. I think you would be hard pressed to find a language where there's no gRPC or protobuf generator. And then you generate essentially an SDK that you can use to interact. And the way this works is you then have these gRPC stubs. That's your generated code that you use in your application. And you have the gRPC server. And then you just, like with other RPC frameworks, you just call functions in the language you're using. And the framework handles the aspects of sending the request and exchanging data under the covers. And it does this in a very efficient way. It has really been optimized for efficiency and performance. Yeah. So there are a few things that stand out. So you can have multiple methods implemented. You have the stream keyword, so it allows streaming of data between client and server, and also bidirectional streaming. So if you use the stream keyword, the communication becomes asynchronous. You have tags for all fields. So the numbering that is an ordering essentially that allows the protobuffer to optimize the data format. So every new field that you add, you increment the number, and then protobuffer knows if this is a new field and it is used to create a map essentially of the fields that are in there and to optimize the message when serializing into a binary format. You have common data types, so the usual suspects, Boolean, string, integer, and so on. You have some keywords like repeated if you want to indicate that this can be an array. Some things can be optional. And when you specify this, the gRPC will then create a binary format for you that is used to send the message back and forth. When you compare this to REST, it supports quite a few features that REST does not support. So both are synchronous, but gRPC also supports asynchronous communication via streams. It has an interface definition language, so what we called endpoint documentation. That is essentially that. Code generation, you can do that in a limited way for REST APIs if you create SDKs based on your specification, but that is not coupled to the actual API. Yeah, both have WebJS browser clients. It's clear for REST APIs. gRPC is not really built for the web. You can do communication from web browsers, but this is not the main use case. The payload for REST, it's whatever you want. I would say 95% plus times it's JSON. For protocol buffers, it's binary. So it's compiled to binary and optimized for efficiency. And if we come back to the initial example of an array, for instance, of JSON objects that all have the same structure, that is not happening with gRPC. We're using protocol buffers because by defining the protofile, it knows the structure of the individual objects and can optimize this. You don't need to have the same structure of the JSON object 100 times. You only have it one sort of as a map, and then only have the actual values in there. So it is a very efficient way of storing the data. Yeah, it relies on HTTP2. If you want to run this on AWS, it's pretty straightforward. There is no managed service. So we take our true and trusted application architecture where we have a load balancer and some containers. As I said, most of the time you're going to use this to communicate between backend services. So the typical use cases, you have some containers in a microservice architecture that need to communicate within a private network, and you want to make this communication as efficient as possible. There are a few caveats. So it creates a tight coupling between the server and the client, which is a trade-off you have to make. That's something you typically want to avoid, but there are some use cases where you might want to trade performance for higher coupling. Depends on the use case. Debugging is more difficult due to the binary format. So you can't just inspect the request and see what is in there. You need the proto definition file to deserialize the binary format and look into what is in there. You require code generators. So every change needs to be a new code generation. You create a new stub that you need to integrate. That makes it a bit more of an involved process to use gRPC in your applications. So what you get is a higher throughput and a lower latency. You define the contract of the API essentially in your protofile, and it allows you to do asynchronous bidirectional communication between client and server. And as I said, the main use case is the communication between microservices. There are some use cases where this is also used for clients. An example I have is, if you remember the Pokemon Go app, where you were running around and tracking the Pokemon. It took a while for those scanners to pop up that allowed you to just connect to the API and see where Pokemon are spawning up. That was due to protobuf, because it allows you also to add encryption. And since they had an encryption key in the app, you couldn't inspect the traffic and just see the API calls that the app was making to see where the Pokemon are spawning up. So it took a few days for someone to figure out the key and decrypt the traffic. So that is also a use case for protobuf that we sometimes see. There are a few alternatives that go into the same direction. I'm not going to dive too deep into this. Apache Thrift, it's the same idea. It has more options. It's more flexible to use. Then there is gRPC. It's hard to read. That is just a drop-in replacement, because gRPC is often considered, the framework itself, quite heavyweight. That is written in Go, that aims to make this more lightweight. They claim they only have 2% of the line of codes, but they also threw away quite a few features. So it's not a fair comparison, because they throw out quite a bit of the features. Just two frameworks or technologies to be aware of when thinking about gRPC. So what does that now mean? Is REST dying? Is REST, is it over? The frameworks we talked about, MQTT is not in there, but they have grown in popularity. So WebSockets was first, then since the 2015-ish, gRPC and GraphQL, they are gaining traction. So more people are interested in it, more using it. That's something I see in my work. People are looking into these technologies to solve particular use cases. However, as you might have noticed, there is REST missing in that diagram, and that is for one particular reason, that the diagram looks like this if we put REST in there. So they're gaining in popularity, but so is REST, and there is no reason to believe that there will be a new reigning champion in the next decade or so, and REST is going to be around for quite a while. But these technologies, they can be a valid alternative for the use cases they have been built to solve. So there's no reason to now go ahead and throw away REST APIs. Keep doing what you do. What you're doing is awesome. Just keep those in mind. And yeah, maybe the next API I'm going to build is based on GraphQL, gRPC, whatever. Thank you. Questions? Yes, sure. Yes, there are quite extensive authentication features with IoT Core. So if you do it yourself using containers, a load balancer, most of the things you need to do yourself. If you use the managed service, there's a number of ways to do authentication with MQTT. Yes, out of the box, they are part of the service. I mean, there's extensive documentation, so depending on what you do, but these services are well documented. There are blog posts out there that describe different use cases. So I think, yeah, essentially all use cases that you should see in practice are covered by those services. All right, then. Thank you for coming and have a great day. Bye, everyone.